Let me just quickly recap what we've done the last time. I showed you this famous Henderson-Hasselbalch equation. Henderson-Hasselbalch equation. And that is an equation that I would expect you to know for an exam or something like that. I would not expect you to know how you get to that. So you don't need to learn that. And I told you that with this Henderson-Hasselbalch equation, it gives a nice relationship between pH equals pKa, that is the acid equilibrium constant, minus the log of the acid concentration divided by the concentration of the base. You sometimes will see it in a slightly different form. It can also be written as pH equals pKa plus log of the base divided by the concentration of the acid. Both equations are exactly the same, and it just simply depends on what's easier for you to learn which way around. Minus acid over base or plus base over acid. I sometimes say to students the easiest way is probably this one here, because you can remember it as Peter Klapper is a positive bastard. Yeah? It's good, isn't it? So, but both versions are exactly the same. And these Henderson-Hasselbalch equations basically tell us about what a buffer is. And a buffer basically consists of a weak acid plus the conjugate base. So we throw two things into this buffer. On the one hand, we throw in a base and also an acid. So, for example, we can make up a buffer if we have, for example, acetic acid. That's the acid. And we add some acetate ions, like that. And with that, we have a buffer. But who on earth gives a damn whether there's a buffer or not? Completely. Right. Now, let's assume we have an acid, and I just simply call it acid. And this acid has a pKa of 7. So it's a very weak acid. We said very high pKa, very weak acid. It doesn't really dissociate very easily. Okay, now we'll just simply take that. Now I want to do a little experiment with you. Let's say we have a pot. This pot contains 1 liter of pure water. You can imagine that. And I add, into this pot, I add 1 milliliter of 1 milliliter of a 1 molar hydrochloric acid solution. Can you imagine that? Yeah? Just take milliliter of 1 molar hydrochloric acid. First question for you. What is the pH before I add the hydrochloric acid? 7? Yeah? Why? pH of pure water. You're absolutely right. So that's pH 7. What is the pH after I add the hydrochloric acid? Can we calculate that? How would you calculate that? Hydrochloric acid, by the way, is a strong acid. Okay. Discuss. How would you calculate what pH this would be? Have we come up with a solution? No? Okay, what do we need in order to calculate the pH of a solution? So pH equals minus log of what? Of the proton concentration. Yeah? And we take 1 milliliter of a 1 molar hydrochloric acid and put that into 1 liter. That is what we said. So can we calculate what is our concentration of the protons in there? What is our volume? First of all, it's a liter, exactly. So the volume is 1 liter. Actually, to be more specific, it would be 1 liter and 1 milliliter. Yeah? But this 1 milliliter is just 1,000th of the liter, so we just ignore that. Yeah? Doesn't matter really. Now, how many moles do we have in there? So, how many moles? Well, do we have moles anywhere in our given? Yeah? What do we have? 1 molar. So it's 1 mole per liter. That's this guy here. And we take 1 milliliter of that. So 1 times 10 to the minus 3 liter. Yeah? That is how many moles we transfer into it. Liters cancel out, and we have 1 times 10 to the minus 3 mole. So these 1 times 10 to the minus 3 mole, or 1 millimole, that is what we put in this liter. So we put 1 times 10 to the minus 3 mole into 1 liter. Well, 1 liter and 1 milliliter, but that's... So our concentration would be 1 times 10 to the minus 3 mole per liter. Yeah? So that is 1 millimolar. 1 millimolar. That's our solution that we have. Can we calculate the pH of that now? Naomi goes like that. So how do we do that? We just simply say pH equals minus log of our proton concentration. We said minus log of 1 times 10 to the minus 3. So the pH would be? Absolutely right. pH equals 3. Yeah? So if I put 1 milliliter of this 1 molar hydrochloric acid into my pot of water, the pH goes from 7 to pH 3. Just by adding 1 milliliter of hydrochloric acid, the pH changes dramatically. Wouldn't you say so? It's a big change. Yeah? Okay, now we do the same thing, but instead of pure water, we take a buffer. So now with buffer. So we take an acid. We take 1 molar of the acid. And we take a base, the conjugate base to that, which is also 1 molar. We mix it together. We have 1 liter of buffer. And our acid has a pKa of 7. Yeah? Now, can we calculate what the pH of our buffer is? Can we calculate that? Well, if Clapper asks this question, then the answer is always yes. Because otherwise it would be pretty pointless to do this. So how can we do that? Well, we use this Henderson-Hasselbalch equation. pH equals pKa minus or plus? Minus, good. Minus log acid divided by the concentration of the base. So, what's our pKa? Can you do that yourself? Can you try to calculate that from this equation? Both acid and base are 1 molar, and the pKa is 7. Give it a go. The pH of that. pH is the same as the pKa? Why? You're absolutely right, Naomi. Sorry? So 1 molar divided by 1 molar is 1. Log 1. Log 1 is 0. So, absolutely. So the pH is?
7.
Yeah. Sorry?
When you said that we've got the 7, pH 7 of this, do they just mean, okay, the pKa is 7, the pH is 7?
In this case, yeah. So, what did you get? pH is 7. So pKa is 7 minus log 1 molar divided by 1 molar. That gives 1. So 7 minus log 1. 7 minus 0. So pH equals 7. Yeah? Happy with that? You got that? So the pH of this solution is 7. It's exactly the same as our water as we had in the first place. Okay. Now we take our buffer and we add 1 milliliter of 1 molar hydrochloric acid again. What's going to happen? What do you think the pH will do? pH will be.
Slightly less.
Slightly less? It would be slightly less. It's a good guess, yes, because we put in some acid. Will it go down to 3? No. Why not? Let's see. Let's see what happens. Right? So we add again protons. How many moles of protons do we add? How many moles of proton do we add? We do 1. We just calculated that, didn't we? We calculate 1 times 10 to the minus 3 mole. Yeah? We've calculated that here when we added it to the water. So we add 1 times 10 to the minus 3 mole of protons. Now what do we have in our buffer? We have 1 mole of acid in the liter, and now we add an additional plus 1 times 10 to the minus 3 mole of the H plus. Yeah? That is what we add. So that would give us, in terms of acid, of protons, it would give us 1.001 mole per liter. That's the acid now. Are you okay with that? So I add the protons to the acid concentration. What happens to the base concentration? Well, these protons actually combine with the base and form the acid. So what happens here really is H plus plus base gives the acid. So in a way, the acid goes up, the base goes down. So for the acid, we had this. For the base, we have 1 mole base minus 1 times 10 to the minus 3 mole. And the whole thing per liter. So we add a little bit to the acid and we take a little bit away from the base. Let me write this nice again. pH equals pKa minus log. For the acid, we said we have 1.001 mole per liter. And for the base, we have 1 minus 1 times 10 to the minus 3 mole per liter. Okay, now let's do calculation. Equals pKa minus log 1.001 divided by 0.999 exactly. Can somebody do the calculation for that? What do you get for this? 1.001 divided by 0.999.
1.002.
So we have, thank you, pKa minus log 1.002. Can you please be so good and calculate log of 1.002?
It's 8.68 times 10 to the minus
pKa minus
8.68
times 10 to the minus 4. So pKa was 7. Can you do 7 minus 8.68 times 10 to the minus 4?
6.999
Equals 6.999. Yeah? So that is our pH when we add 1 milliliter of this hydrochloric acid to the buffer. Sorry? It is a minute change. It is just tiny tiddly bits, this change. Remember, in water, we had a pH going from 7 to 3. In the buffer, we have the pH changing from 7 to 6.999. Do you see what the buffer does? The buffer prevents the solution to change pH. A buffer resists changes in the pH. It would be similar if we add a base. If we added a base instead of the hydrochloric acid, the concentration of the base would go up and this concentration of the acid would go down. But again, the change would be very, very small. So when do we use buffers? We use buffers in a system where we don't want any change of pH. Where a change of pH would be a bad thing. Why could it be a bad thing, a change of pH? Why? Why does it denature proteins? What does it mean? Say it loud, please. You are so right.
It changes the ionic bonds in the tertiary structure.
It changes the, I repeat that, it changes the ionic bonds in the, probably in the secondary structure as well as in the tertiary structure. So it changes ionic bonds. If the pH changes dramatically, then these bonds are changed. Why? Why are these bonds changed? What do we have in proteins? What do we have in proteins? Amino acids. Okay? What does an amino acid in a protein usually look like? It has amino and carboxy groups. Excellent. So we have CO, we have NH, C, NH, something like that. And then our amino acid, which is in these peptide bonds, you recognize this as a peptide bond. That's the backbone of your protein. But then the amino acids, some of them have charged side groups. So it could be CH2, and something is hanging on there. For example, an SH group. Which amino acids contain sulfur? Loud? Cysteine and? Methionine. Yes? Which one would that be? Are you sure? Cysteine? Yeah, why? Because in the methionine it would be an CH3 group. Yeah? So this one would be cysteine. Now, this SH group, it can give off a proton. Yeah? For example. So it's an acid. But the pKa of this acid is pretty lousy. It's in the range of 8. So that's the pKa. Now if I have a pKa of 8, I can ask the question, what does my cysteine residue do in different environments? Let's say I put my protein in pH 1, pH 7, pH 9, pH 12. And I want to see what happens to my little cysteine there. How can I deal with that? Again, we have the lovely Henderson-Hasselbalch equation. So we can calculate what the cysteine does. So, for example, at pH 1, pH equals pKa minus log of the SH form, that is the acid, divided by the base form. Yeah? Now we know that the pH is 1, because that is what we put it in, equals 8 minus, what is this bit here? You don't need a calculator. 8 minus 7. So, log SH over S minus is 7. So what is the true ratio? Well, I take both sides 10 to the power of. And I have the ratio of acid to base, or SH to S minus, equals 10 to the power of 7. Or I can write this as 10 to the power of 7 to 1. At pH 1, I have one molecule in the S minus state and 10 million in the SH state. Yeah, that is at pH 1. Does that make sense? Now try to do that at pH 5 yourself. How much of do we have of the SH and the S minus at pH 5? pKa pKa is 8. Do you want to do it together, or do you want to try it yourself? Got it?
Yeah, I get it now. So basically, the more the higher pH, the less you've got in the traditional, where it's not been associated, therefore it's becoming more and more unhappy.
So again, you use the Henderson-Hasselbalch equation.
That basically means every 1,000.
You have your pH 5, your pKa, minus this log acid over base. You know that this must be 3. This log acid over base equals 3. 8 minus 3 equals 5. Yeah? And you take both sides 10 to the power of to get rid of the log. So you have acid over the base concentration equals 1,000 to 1. So 1,000 molecules are in the acid state, in the SH state, and 1 molecule is in the base state. Yeah? Does that make sense?
How did you know that acid over base is 3?
8
8 minus something is 5. Yeah? So this something must be 3. Okay, here's another one for you guys. pH equals, say, 7. pH is 7. pKa is 8. What is the ratio of acid to base?
Cysteine and water should be really messed up.
So again, we do this thing. pH, pH 7, pKa 8. 8 minus something is 7, so this something must be 1. This log acid over base equals 1. And therefore, the ratio of the acid of the SH to the S minus is 10 to 1. For each molecule of the S minus form, I have 10 molecules of the SH form. Yeah? pH equals 8.
So there'll be no molecules on the SH.
No, we won.
Loud. 1 to 1.
10 to the power of 0 is 1. I get everything right.
My best friend Katie's going to
Okay. We do exactly the same thing. pH, that is 8. pKa is 8. So log of acid over base is 0. Yeah? And if it has 0, I take both sides 10 to the power of, log of 0 is, or 10 to the power of 0 is 1, so I have 1 to 1 ratio. I have exactly the same amount of the molecules in the SH state as they are in the S- state. So I have a 1 to 1 ratio. What happens if the pH is 9? And the pKa is 8. What do you reckon?
Wait, does that mean you have to use the other equation, the plus?
No.
Be minus minus, so...
No, you don't. You can still use the same equation.
Minus 1 is, will that work with the equation? Potentially minus 1.
But then there's S minus still.
It would be minus 1. Yeah. So what is this bit here, this log? It's minus 1.
Yeah, but it would be SH over S minus.
Leave it like that. Leave it like that. Huh?
Yeah, 10 to minus
10 to the minus 1. Yeah.
The answer over 1.
Yeah.
Will it still be that over 1? Will it be
What you get is 10 to the minus 1 divided by 1. Yeah. And now what you do is you just expand this fraction by the factor of 10.
Yeah, to make it.
So you have 1 on top and 10 down.
So you have more of the equation.
Yeah. So what do we get? Log of SH divided by S minus. What is that? When you solve that? It's minus 1, isn't it? So you take both sides, 10 to the power of, and you get SH divided by S minus is 10 to the power of minus 1. Yeah? Or 0.1. That's this one here, the 10 to the minus 1. 0.1 over 1. Or I can expand this, because that's a little bit inconvenient to imagine. I can't have 0.1 molecule. I just multiply both parts by 10, and I get 1 divided by 10. That would be my ratio. Yeah? So I have 1 molecule in the SH form and 10 molecules in the S minus form. Now, if a protein can do that, we can imagine, and that was your response earlier about the different ionic bonds. Let's say this protein let's have a nice protein here. And this protein is held together by an S minus, and this minus forms an electrostatic interaction, let's say with an NH3 plus here. Yeah? And it's held together by this, so S minus, and here we have so we have an electrostatic interaction that keeps that protein in its nice shape. What happens if you decrease the pH? If you decrease the pH, sooner or later there comes a point where this S minus becomes an SH. When the pH goes down, when the proton concentration goes up, we have an SH. Can this SH still form this electrostatic interaction? It can't form it. So what happens, in a way, we no longer have this nice interaction with this ammonia group. And it's a little bit like, you know, this electrostatic interaction is like a push button. It holds the protein together. But if this electrostatic interaction is no longer there, the protein simply collapses. Yeah? The protein denatures, can't do its job anymore. So that's why it's so important to have a buffer system. Because even if we add lots and lots of protons or hydroxide ions to a system, the pH wouldn't change dramatically. And our proteins would stay intact. That is why the cell and why your body have developed very sophisticated buffering systems. So that whatever happens to the body, whatever happens to the pH, it will stay regulated. It stays so that there's no damage done. Yeah? I will give you some medical implications on Thursday.